Good evening, everybody. This is Obi-Wan Piz for In Simplex Pachinko. We are going to be doing some math tonight. I did change the stream name, although I'm not sure exactly how much we're going to be doing on rings because I'm not really all that knowledgeable on it, quite frankly. But at the very least, we'll have some fun tonight. We'll pull on some threads if anybody has anything they want to ask. Particularly, there are plenty of different subjects that we have been working on, and we might as well, just for the moment, work back on elementary geometry, although I don't know if I actually have my book right here. Go figure. Huh. Yeah, it's probably over by the door. Alright. Well, let me just check, I guess. Yep. Right, over next to the door. Let me also check volume. We're doing. Alright, so I think this probably is about the right setting. If anybody is hearing me drowned out, please feel free to comment. Check real quick here. Do we talk about rings? We do not talk about rings in this book, so oh well. I gather it's not actually that difficult. It's just me being kind of a pain. Okay, so Theorem 9 was looking at the reciprocal. The product is the product of the reciprocals. And we proved that last time we were kicking around some of Moise's book here. So, man, I am running out of spaces to put stuff. That's fine. All right. So in Theorem 10, we have the negative of the sum is the sum of the negatives. And in this particular way, we want to, again, prove the negative of a sum, a plus b, is going to be equal to the sum of the negatives of these numbers, negative a plus negative b. All right, and again, without looking at the proof that's given here, trying as best I can to not pay attention to it. What is it that we have talked about? we have multiplication of negatives. We do have, right, negatives of negatives are the originals. I don't think we need any of that. Do we have negative of something is -1 times? I'm not sure that we do, technically. 0 has no reciprocal, cancellation laws. Yeah, okay. I did that, but... Oh, that was it. Yeah, okay. Negative a times negative b is just equal to ab. Okay. Okay, so this is the additive inverse of a plus b. So what that's going to mean is that if these are equal, let's go with proposition A up here. So given A, that means that instead of writing negative parentheses a plus b, we could write all of this stuff instead. So negative a plus negative b plus parentheses a plus b is going to be equal to 0. So this is supposition, right? We're not sure that this is going to be the case, but we know that, right, the negative of a sum of two terms, a and b, so a plus b, the negative of that thing since it is the negative of something, then that original thing plus the negative of it should be equal to 0. So that's true, always, no matter what. Then we're saying that given that A is true, this top part here, that negative parentheses A plus B is equal to negative A plus negative B. Given that that is true, then we could say that negative A plus negative B plus the original parentheses A plus B here is going to be equal to 0 as well. So these should work out that way, which this right here is going to allow us to take out the parentheses. We don't need them. So here we can get rid of the association that exists around this particular set A plus B. It's all addition. There's nothing that we're multiplying in or anything like that. So, all right, and then we're saying here that we can commute these things in the middle, specifically those two. But so negative A plus negative B plus B. It's going to be equal to 0. We can do this by commutativity. And then negative A plus A is going to be 0. Negative B plus B is going to be 0. We're adding these things up and we're getting 0. This exists by additive inverse. And then 0 plus 0 is equal to 0 is a true statement by something that we showed back over here somewhere. Alright, there's some sort of sum identity that told us that 0 plus 0 was just 0. Huh. Additive identity. Right, never mind. Oi. Promise I'm okay. Alright, in the Moyes book, Theorem 11 says that for all x in the real numbers and a, we know that x minus a times x plus a is equal to x squared minus a squared. Okay, so now we want a proof of this. Woo. Okay, so question, do we have distribution? Yes. We have a left distribution right here. Says that if we had okay, we're doing it forwards instead of backwards, but whatever, it's the same thing. Do we call distribution anywhere else? Distributed property here. Yeah, distribution, right there. Alright, so for any R1 times parentheses R2 plus R3, Uh, Good evening. Delau Dons Dela. Let me know how you would like that pronounced, if any. So I am Obi-Wan Pez. This is N Simplex Pachinko. Good evening and welcome. We are doing some. So this is actually, well, I guess technically it is. This is out of a book that I had for my junior year of math education. So we had a particular geometry for teachers class that was sort of like real analysis light. We all had to take it. So I decided I was going to go through this and do some building from basics, starting over, and try to make sure that we can get our algebra on the proper footing. But if you have any questions, or if you have any suggestions on stuff you'd like to see, or things you think are really awesome things, let me know, and we'll put something on. Okay, so here we can take the thing on the left and distribute it into the other things on the right. So we're going to have an x minus a multiplied by x plus an x minus a multiplied by a. What's my favorite math theorem? You know, it's probably going to take a while for me to remember, but there are some really nice ones. Let's see, I was reminded the other day of yeah, okay, so like I actually proved the change of base formula in high school, and you know, unprompted. I should have taken it as a hint. This was definitely going to be where I wanted to be. And though it seems like super basic now, it at the very least it was like the thing that kind of caught my attention and said like, oh, I can kind of do this stuff. You know, nothing. It wasn't anything terribly difficult. It was just your standard log base a of b. And so let's turn that into something else. And so I said, all right, let that be y. This is going to be, you know, a to the y is equal to b. And then I want to change this to a different base, so I'm going to take the log base c of both sides. Our y gets knocked down, so this becomes y times log base c of a is equal to log base c of b. And then this gets knocked over here, so y is equal to log base c of b over log base c of a. I had that backwards. Nah, whatever. It's cool. And then our y here is equal to log base a of b equal to log base c of b over log base c of a. I'm not sure I really necessarily think that this is like my favorite or anything, but it was certainly, again, something that just kind of proved to me that, yeah, I can do the algebra. I actually do have the chops for this. And like I said, I probably should have taken it as a hint that I wanted to do something more mathy than even what I was thinking about. At the time, I was trying to be a physics major with a concentration in astrophysics, which would have been really nice given all of the crazy stuff that's going on these days. However, I did go on to get my master's in applied math, and would have also been a really good time to get into astrophysics because I was also doing machine learning. So I could have conjoined my astrophysics with my newfound love of machine learning and figured out some really awesome stuff, but c'est la vie. I also really like teaching, so. Oh no. Over the winter, you mean, specifically? Playing them? Good evening again. Uh-oh. Come on, there we go. Alright. Alright, and here. So... oh no. Very bad. How... when do you all start? It should have been today. Oh no, your quarters. Yeah, okay, never mind. Is that online again? Okay, we didn't technically do right distribution, but... no! Don't do that. Nah. My linear algebra stuff here. It's all at school. But I do have my engineering book. Aaron Krasik, Advanced Engineering Mathematics. This was the book I was required to get for my master's prerequisite class, just to make sure that I did, in fact, know all three of these classes: linear algebra, multivariate calculus, and differential equations to the undergraduate level. I had to take this class. This was the, well, second time that I took a differential equations class, which was like ODEs. You know, just solve ODEs. I ended up taking a basic ODE class 3 times. I passed all of them. It was just that I had to take the ODE class as a member class of my linearity class, which was a full year-long class for 12 total credits. It was, again, multivariate calculus, differential equations, and linear algebra, multivariate. I go in a different order every time. Linear algebra, multivariate calc, and differential equations, all at the same time. Yeah, 6 credits per semester. And then when I got mono during semester number 2, they couldn't separate that out and be like, well, you know, you finished like half of it, so we'll give you like credit for these 2 classes and you'll just have to retake the... No. Nope. Couldn't do that. So they had to wait. They said you could either take all 3 of them again, or you could just wait until the next time it cycles around and then take the second half, the second semester of the year-long course. And I was like, yeah, let's just do that. So I have signed up, I suppose, for linearity again, only half a semester that time, but whatever. The prerequisite course for my master's, the basic ODE class for my master's. So that is 4 ODE classes that I had to sign up for. Where it was specifically ODEs only. And then we did partial differential equations and nonlinear differential equations, which were really awesome. But again, we kind of started from the beginning, and we're like, here's how to solve ODEs, and I'm like, like I get it. Although I will say, we did prove that the 3-body problem is impossible to solve in nonlinear differential equations. That was pretty cool. Like, oh, you want to solve the 3-body problem, do you? Lol. We had an older gentleman at our church who the first time that we went, I looked kind of like this, maybe a little bit longer in the beard, and he kind of hobbles up to my wife and says to her, "Tell your husband that he has a beautiful beard," and walks off. And she's like, "Okay." After a while, we got to talking. Turns out that he had worked at the Johns Hopkins Applied Physics Lab, which is where we both got our masters. And he did like aerospace engineering and stuff like that. And at some point, fairly close to when he and his wife moved into assisted living, his was pretty much at that point hospice, because he was passing. But one of the last few conversations that we had, he came up and he said, "No, I just want you to know that I'm confident you can solve the 3-body problem." And I'm like, okay. I was like, no, that's literally unprovable, and I have proven that it is unprovable. But I'm not going to smash your heart into little bits. Blendland, if you do have any particular questions, let me know, because we can do some basic linear algebra stuff. If you let me know what the particular subject is. Obviously, I'm not going to do your homework for you or whatever, but, 271 to 363, goodness. Just a straight 100 pages on linear algebra. Alright, let's finish this one. So easy thing to do here is we can say that we've got a lemma right distribution. So for some real values, R1 plus R2 times, parentheses times, R3 is going to be equal to R1, R3 plus R2, R3, multiplication between them. So here we can just say, we can do commutativity, and this is now going to be R3 times R1 plus R2. Then we do left distribution. Oops. Multiplicative commutativity. Also known as Monsieur commutativity. And then here we have R3 times R1 plus R3 times R2. And this is going to be left distribution. And then we do R1 times R3 plus R2 times R3 by multiplicative commutativity. So right distribution works just as well as left distribution. Ta-da, there we go. So here we could do right distribution as well. This is going to be x times x minus a times x plus x times a minus a times a. Probably should have had that on the next line. Anyway, whatever. It's all cool. It's going to be there. And this is equal to x squared minus a squared. So same thing there. X times x is x squared. Negative a times x plus a times x minus a squared. This is going to be our multiplicative commutativity. And, you know, rules of multiplication becoming exponents and all that, but whatever. And these two things make a 0. So x squared plus 0, nope, minus a squared. That's going to be additive inverse. And now this is just x squared minus a squared is equal to x squared minus a squared. And that is also additive inverse. Oh no, sorry, that's additive identity. All right, so proved.
I don't know what y'all think, but I think that's pretty.
All right, so the good news on this one, we're done with the theorem. So this is chapter Chapter 1, Section 2, essentially. 1-1 up here and 1-2 down here. This gets us everything from 1-1 and 1-2, and now we can do the problem set when we feel like doing this again. 1.2. really, I shouldn't do that.
You guys are so good at that.
Okay. So looking at tonight. So we have basic matrix theory, which comes at the beginning of linear algebra. So a matrix is going to be an array of numbers arranged in usually m rows and n columns. So that's not what I want. I want that one. So in this particular case, this would be a 6x5 matrix. Rows by columns. You know Megalomorph's working on a pun. Just waiting for me to talk. Say something. Alright, so some sort of arrangement of numbers in m rows and n columns, and each individual value is going to be, if we say that this is like matrix A, typically we put the dimensions right next to it if we want. You don't have to, but this is going to be A in the first row and first column, A in the first row second column, A in the first row third column, A in the first row fourth column, A in the first row fifth column. A in the second row first column, A in the second row second column, A in the second row third column, A in the second row fourth column, and A in the second row fifth column, etc. There's not that many in this particular case, but whatever, it's fine. All the way down to A in the sixth row and first column, A in the sixth row second column, A in the sixth row third column, A in the sixth row fourth column, and A in the sixth row fifth column. Oops. Okay. So once you've got this, all of those individual elements can be literally any number you want them to be. In a generalized matrix that is, size m by n, then you've still got A in the first row first column, A in the first row second column, etc. But then it starts deviating a bit because nobody's got time for that. We could just say that, okay, this jumps to the bottom. We have A in the mth row first column, A in the mth row second column, and then eventually this all goes down like this until we get A in the mth row nth column, at the bottom, A in the first row nth column at the top, and A in the first row, second row nth column in the second position there, and again dot 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 between all these things. So this is very much the generalized look of how an m by n matrix should look. For matrices, we want to make sure that, you know, standard math works. So for matrix A plus B of size m by n, first of all, they have to have the same dimensions, because what we're really doing here is we're taking basically two spreadsheets and then merging them and saying we want the sum of all of these individual values. So if you have data that does not include things that are of the same type, it doesn't make any sense. I will think of these, you know, to my dying day as something that has to do with spreadsheets, because it's just how I started learning it. So this is also going to be m by n. This is going to be a11 plus b11. Next one over is going to be a12 plus b12. That's going to continue out all the way to a1m. Nope, 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 nope. 1n plus b1n. Second row is going to be a21 plus b21, a22 plus b22, dotted all the way out to a2n plus b2n. And that will continue all the way out to am1 plus bm1. Next one over is am2 plus bm2, all the way out to amn plus bmn. Okay, so for addition, what we're looking for is that these things have to have the same size. Not point-wise. Okay, so another way to call this is element-wise. Addition. Now there is the possibility that there is some multiplication, which is an element-wise multiplication. But unfortunately, that is not how we're going to be doing multiplication, generally speaking, with matrices. Also known as the Hadamard product, entry-wise product, Schur product, Khatri Rao product. Oh man, there's a lot of different names on that one. So typically this is not a star, this is not a like multiplication symbol that we usually use. It is essentially a hollow circle like that, which normally I would think, oh, that's composition, what are you doing? For what we're doing in the context of matrices, that will actually be, oftentimes at least, the element-wise multiplication. Or it could also be written as a product B like that. It looks like a bullseye. That's going to be our element-wise multiplication. We don't typically use this. There are individual cases in which it is actually, like, it makes sense to use it, so you can do this in MATLAB or something like that. But again, we just don't use it. So more typically what we want our matrix multiplication for is something like a system of equations, where if we have, you know, A times an X vector equaling a constant vector, C vector, something like this. This is going to be a representation of a system of equations. So systems of equations are pretty much what we've always used matrices for, and that's why it's the most popular type thing for at least, like, you know, Western European descended mathematicians. You know, mathematicians who learned in the West, anyway. The multiplication that we use is almost exclusively used in the sense of systems of equations. So the way that we do that essentially what we have is our A11, A12, A13, out to A1N. Every time, man. Here we have A21, A22, A23, A2N. To AMN. And yeah, it's fine. A2N, A3N. M. These are supposed to be M's. M1. Man, I just don't do this enough. Notations kind of throw me a little bit. M2, M3, all the way out to Mn. Okay, this is multiplied by an X vector, which is going to be something like X1, X2, X3, dot, dot, dot. This has to have the same number of variables here as we have rows in this matrix here. Nope, sorry, columns. same as the number of columns we have in this matrix here. Because what we want is something like, again, A11 x1 plus A12 x2 not squared. Plus A13 x3 plus all the way out to, this is going to be x sub n a sub 1n times x sub n is equal to, and over here we have a column vector of however many equations we have here, what their constants are equal to. So this is going to be C1, C2, C3, all the way down to Cm. So this is going to be C1. Then we have A21, x1, plus A22, x2, plus A23, x3, plus A2n, xn equals C2. This is then going to continue till we get C sub m here. This is going to be A m1 x1 a m2 x2 plus a m3 x3 plus plus a sub mn x sub n. So systems of equations, this is how the multiplication works for most matrices, all that we want to look at. We're going to take the entire row, line it up, and multiply the entire column of the next matrix. That ensures that the first item in the first row will be multiplied with the first, or the item in the first row in the second matrix. Misspoke slightly, it's fine. The item that is in the first column in the first matrix is multiplied by the item in the first row in the second matrix, etc., etc. Going all the way down, we make those individual multiplications, and then we sum all of them up. And that is what we get on the right. So this is an m by n, this is an n by 1, and this is an m by 1. One of the ways that we had always looked at this in high school was we said, like, okay, you write out whatever your matrices are. We're trying to multiply. And you first have to make sure that the center ones will match, because again, the number of rows in the second matrix needs to match up with the number of columns in the first matrix in order to get this multiplication correct. So there have to be the same number of elements in the row of the first matrix as there are in the column in the second matrix, which means the number of columns in the first matrix and the number of rows in the second matrix have to match. So those are our inner numbers here, n and n. Those are good. And then we take this thing and we say, what size is the resultant matrix going to be? That's going to be an m by 1. As long as our n's match up here, the outer numbers will give us the size of the resultant matrix. Alright, so again, the whole point of this was to make systems of equations easier. And we were saying that, well, since we're doing this multiplication of all of these a constants by our x vector, and we're getting all these c constants back, wouldn't it be really nice if we could invert this matrix here, do a multiplicative inverse, and come out with just the variables on that side? And yes, it would be very nice if we could do that. There are only certain conditions under which it works. Most famous probably of which is that it needs to be a square matrix, first of all, in order to make sure that the number of rows and the number of columns are going to line up. So we can look at individually. We have like, can we make this into a field? So the first thing to do is look at, do we have an additive identity? So is there something where you take an m by n matrix, you add it to something, and you end up with that same m by n matrix? Well, yes. So first off, it needs to be m by n in size. It needs to be our identity matrix, which on the individual terms all throughout this whole thing, they have to stay the same. So if we just added them like we did up here with our a and b, then pointwise addition, we just have to keep adding zeros to everything. So I is going to be equal to a matrix with all zeros. Okay, so I is just going to be an m by n matrix, which is full of zeros. That's it. It's just a zero matrix of the same size. All right, similarly, what about additive inverse? Well, to get additive inverse, you need an m by n matrix to be added to something in order to get your zero matrix. Well, if we're adding, it needs to be the same size, so this is going to be an m by n. It's going to be an m by n at the end as well. Oftentimes we could put like 0 like this, and we just know what it means. It's going to be all zeros for an m by n size, or we can say it's a the result has to be an m by n matrix that is all zeros. So what's that going to be? Well, it's going to be individually all of our individual terms, negative a11, negative a12, right? Negative A21, negative A22, all the way down then to negative A M1, etc. So this is the same as just negative A as m by n, which also makes sense notationally because whenever we add two things, which have opposite sign, then we end up with that zero matrix, or a zero element from before, whatever the additive identity was. So additive identity, additive inverse, this is all super easy stuff. Right, then we start looking at multiplication. Do we have a multiplicative identity? So if we have a multiplicative identity, we start with an m by n matrix multiplied by something to get us the same a sub m by n again. Well, first of all, it's going to have to match the middle number. So it has to be an n by in order to make sure that we can multiply the same way we did up there. All right, so it has to be n by, and then it also has to match, again, this second location here needs to come from here, so that has to be n by n. Right, so match. And then dimensions of resultant. So it needs to be an n by n matrix. All right, so what does the identity, multiplicative identity, going to do for this? Well, it can't be all zeros because that would just eliminate everything. Yep. So an n by n matrix that's all zeros, that would be the same as the additive identity, would eliminate everything and just make it all zeros. So we don't want that. What we want instead is that the specific row and column of every single individual location is exactly 100% the exact same for any particular element all the way through the whole thing. So we have to go to our little thing here where we said, okay, this is going to be A11, A12, A13, all the way up to A1N, A21, A22. You don't have to necessarily do this, but you get the idea. Okay. So now we need to multiply by something that is n by n in order to get the exact same thing back. Okay, so in order to get the first row and first column to remain the same, then the element from the first row needs to be multiplied by the first element from the first column. And it needs to be the same for that individual number. So it's going to need to be a 1. Whereas all of the rest of the terms going across here need to go away. And remember the way that this all works here, it's all summed. So since we're summing up all of these numbers, the rest of them are going to have to be zeros, going all the rest of the way down, all zeros. Okay, so this is going to be 1 for the first element, and then all zeros for the rest of the stuff that we're multiplying. All right, in order to get the second position here, in order to get this exactly 100% identical. We're taking the first row and the second column. So first row here multiplied by the second column here, and we need this second element to stay the same, and no others. So the first element needs to be a 0, the second element needs to be a 1, and then everything else is going to be zeros all the way through. This is going to be a little deceptive, but because of the dot dot dot. This is all going to be this is all zeros. All right, like I said, a little deceptive. All right, in order to get the third, first row, third column to only have the first term here, again, this is going to be the 1, 2, 3, third position. So this is going to be a 0 for the first position, a 0 for the second position, and a 1 for the third position. All the rest of everything all the rest of everything else needs to be zeros. As I said, this is going to be a little deceptive. And in order to get this last first row, last column, nth column to show up as exactly the same number, we need to multiply the first row by the nth column, and then only the last term can count. So that's going to be a 1, and like everything else is going to be zeros everywhere else. So the multiplicative identity, at least for the first row, it appears, is going to end up being a diagonal matrix, zeros everywhere except along the main diagonal. A11, A22, A33, all the way down to ANN. Sorry, no, I. Right, this is I11, I22, I33, all the way down to INN. All of those along the main diagonal. Main diagonal. I'm backwards. All those along the main diagonal are going to end up being 1s. Everything else is going to be zeros. Everywhere. Okay. So everything on the main diagonal is 1. Everything else is zeros. All right. Bertram, good evening, or at least good morning, I guess. Hope things are treating you well. Okay, so an identity, a multiplicative identity matrix is going to be main diagonal is 1, everything else has to be 0 everywhere else. All right, what about multiplicative inverse? Yeah, that's my face. I'll just do that. So this says we have an A m times n multiply by something, which again we can term it a inverse like this, and say that we need to get back to an identity matrix. Well, the middle term has to match, so it's got to be an n by, and then it's an identity matrix, so it has to be a square matrix because we just talked about how that was working up here. So it has to be an m by m. So that fills in this place. That's all well and good. However, we also then want to look at the possibility that this multiplicative inverse could be applied on the front of one of these matrices as well, not just at the back like it is here. So we also want this to be equal to A inverse times A. It's not on there. Well, there's only one way that that can actually happen, because again, here if we do it as an m by n, and this is an n by m, again, here our m's match, but then the n's don't match this, or at least not necessarily. So the only way that this is going to work is if m and n are the same thing. So A has to be a square matrix too. That was a Mario 3 sound. That's also a familiar song. That's Final Fantasy VII. It's a variation on Cosmo Cannon. Interesting. So multiplicative inverse can only really work if A is square. Because again, we want this inverse property to work out, that we end up with the same identity matrix at the end. So stepping back to what we did up here, where we looked at like A times X vector is equal to C vector. No, it's just stacked up over 20 some odd years at this point. So if we've got a times x is equal to c like this, again, what we want, I liked sociology. That was kind of interesting. Psychology was another possible option. Geography seems like it's not a social science so much as it is a, like, I mean, I guess if they talk about like geography including political boundaries and stuff like that. I was actually going to take, well, I guess technically that was history credit rather than social science, but um, they were separate at my school for some reason. So we had like a history and a social science. Why? I guess what's your major? That's the other thing, right? Or is that a requirement, like, no matter what your major is? I know at our school it was sometimes like you didn't have to take it if your major was a part of like this branch, but it was okay if it was over there. So here, the only way to actually move A, our matrix A here, is to multiply on the left by A inverse, which means that we have to multiply the other side on the left by A inverse. Depends. How's your trig? So, I mean, you don't necessarily have to know your trig really well, but it would be an advantage because you're going to have to learn how spherical coordinates work. And if you feel you're pretty comfortable with like spherical coordinate calculus, that would be really great. You would be at a distinct advantage above those who have not taken it, who have not taken multivariate. Because when you're doing all of these calculations for trying to figure like azimuth and azimuth and elevation, you're working on a system that is using spherical coordinates. So you're using essentially a radius, which is going to be like the size as it goes out to the, you know, the sky. You've got your radius, you've got your azimuth is coming across, like across the ecliptic. How far are we going from 0 out to 180 degrees that way? It's like, you know, you stop here, that's about like 50 degrees or something like that, azimuth. And then your elevation starts from the horizon and goes up. So starting from, I can't do it. Okay. Oi. Starting from like here, you'd say, okay, I've got my azimuth coming across the ecliptic here, and then the elevation is coming up here to meet it that way. So what's this angle here from the horizon up to this location? So you can end up going like 50 degrees that way, and then, you know, a 30, 40 degree elevation off the horizon. And by finding these two angles, the elevation and the azimuth, you can essentially just say like any point on the sky is based on this. And yeah, the only thing that you're missing for spherical coordinates is radius, but you just kind of assume that everything is on a dome, infinitely far away, or, you know, the size of the solar system, or whatever you want to call it. It doesn't really matter until you need it. So when you start talking about like the actual distance to like Jupiter and Saturn and things like that, then you can figure out like where things are at any moment in time, and that gets to be that gets to be all sorts of crazy. All right, so here this is going to be an I size matrix multiplied by x vector is equal to A inverse times C vector. I times x, these are of the appropriate size. Again, we force it so that they are of the appropriate size. So astronomy is looking at telescopes and stuff like that to figure out where the stars are. And like what kinds of stars are there. Like what properties do they all have? The planets and stuff like that. It's really cool. I mean, it might be a small challenge, but I don't think you're gonna, like, students have to be able to enter this without calculus. So, me personally, I was really into astrophysics. Basic physics might be one of those classes you really should take. You know, mechanics. It does get somewhat annoying sometimes having to draw like force diagrams and things like that, but overall, it really is a good thing to be able to like pull it up and just say like, you know, here's how to set up a problem. And here's how to think through solving a problem. Things like that. Which if you have the math background for it, it's pretty good. If you take, because you're already past, I mean, maybe you only need that one. So, could work. And at this point, are you just looking for like a physical science gen ed requirement? Yeah. So my physical sciences, I ended up taking both chemistry and physics because I was originally slated to take physics anyway. And then they were like, well, you can't take that because you're a major in physics. So I was like, okay, well, I guess I'll pick chemistry. So I did chemistry as well. And then I switched majors into math education. They're like, why do you have 2 sets of physical science credits? Because that's not going to count. And I'm like, I switched majors. So geography is not going to be a physical science. Geology will be. Yeah, there's a lot of equations, but honestly, if you know how to do unit analysis, if your math is decent, and I mean like basic algebra, then it doesn't really take all that much effort. If you want to figure out like torque. You're going to have something like Newton meters, and then Newton. Right, so this is a force, and this is a distance. So torque is a kind of work. Like a kind of work. I mean, yeah, but which also people use foot-pounds for, which is a terrible measurement, but foot-pounds, could use those, and then again it's a force times a distance. What about cross product? Level arm cross force? Haven't really done anything with that, I don't think. But like, this is one of the things that I keep telling my calc students is like, if you know how to do unit analysis, you've pretty much got the problem set up. You just need to figure out where these individual things are. So, like, I was thinking of something the other day. I was trying to get home, you know, a little bit faster. And I said, so if I drive 10 miles an hour faster than I am currently driving, how long will that shave off the trip? Yes, actually, I'm teaching both Calc 1 and Calc 2 and Pre-Calculus 1. So the functions half of the course. So I was like, you know, standard, here's what I've got going on now, and then here's me adding 10 miles an hour to my speed. So if I wanted to do this as t equals RT, then what I want is my distance is going to remain the same because I'm still traveling the same distance to get home. My rate is going to be R plus 10, and then my t is just going to be like t2. I don't know what it is, so it's going to be some function of t1 and how, right, like what is it going to do? So as near as I could figure, we could set it up either as a proportion, set our d's equal to each other, and say like t2 is going to be equal to rt1 over r plus 10. And if we let r be 60 and t1 be this was going to be 6/7 of t1. Whereas at r equals 65, this would have been t2 is going to be equal to 65 over 75 is going to be 13/15. So let's see, 6/7 is about 85.7%, and 13/15 was going to be about 86.6%. So if we were doing 25 minutes to get from one place to another, that would end up reducing the whole time by about 3.5 minutes. And if we're doing 65 for 25 minutes, that would end up reducing it by 3 1/3 minutes. 3? Yeah. But that's over the entire 20 some odd minute trip. So like 21 point, let's go with the average here and just say 5 divided by, nope. No, it's the difference of these things. So 3 1/3, 10/3. Out of 21.6. It's actually out of the 25-minute whole trip. 2/15 is about 13. So it's like a 13%. Of course, it's the 13% reduction, right? Because that was, yeah. Okay, so the real question that I was thinking was like, how long is it going to take to reduce 1 minute off of your final trip if you drive 10 miles an hour faster? So like, we want to fix T1 how long would I need it? See, this is why sometimes it gets a little crazy. Um, so the time remaining should be basically your distance divided by r bar, your average speed as calculated by, maps or whatever. So I want to take this time and I want to subtract it by 1 and get that to be the same as this ratio, I think. Is that a thing? order to reduce the remaining time by 1 minute, we have to take our current rate of speed, multiply by t1, divided by... No, because that's not a distance. It's not a ratio. No, wait, hang on. But it's still a time. Okay, we're good. Maybe. Maybe. What does this do? That is in hours, so that's not going to work. 1/60th. Seems much more attainable at the very least. It's like if we're gonna get T1 to be the thing that we're trying to solve for. I don't think that that's gonna work, but let's see what happens. dr plus 10. Okay. Times 60 minus r bar r plus 10. That's gonna be now that time needs to be equal to R2. So this should be T1. As terrible as that is. Alright, I think that R bar can safely be assumed to be the same as R. That just would have been the average speed, but this is going to do something awful, isn't it? Love it. This would have been... No. No. That 60 can't be there. Still going to be attached to this one. But it does divide by r, doesn't it? Which means that r needs to also go away. It needs to stay where it was. Okay, so we multiply by r plus 10. Get rid of it over here. It's going to be negative r plus 10 over 60. Here we have a d times r plus 10 over r. And then we also need to divide by r. So we have an r there and an r there. So it depends on a lot of stuff. I'm surprised that I did not somehow walk myself into a corner. D over r squared minus 1 over 60r all multiplied by r plus 10. Oops. And I don't know how many times I kicked my keyboard, and I'm going to wonder what I'm doing to my Linux box. I had to take like all of the... Every time I stream, I swear I just have to switch things back and forth. Yeah, because all of my... I've moved my... or kept my math streams here on PC because or Windows box, because it's just easier to work with the app version of MS Whiteboard. I've looked around at other stuff, and it's possible that I might be able to do something. A lot of people have said, don't do OpenBoard, and I was like, well, that's what I was going to do, so alright, guess we're not doing that on Linux. The online version is awful. We've done that a couple of times here on stream. Basically, the lag is just incredible, and anytime I try to write something, it's just a disaster. T2 on the right, the original thing on the right, is equal to the other version of T2 here. It's T1, which is d over r, minus 1/60th, subtract a minute. Distance wouldn't necessarily have to be the same if we're saying we want to sustain 10 miles an hour until we lose a minute off the ETA. So d over r minus 1/60th is going to get us the whole remaining bit of the trip. And same thing for... Alright, so this is going to be the same thing for this one. You know what, let's just do that. Let's not make it super complicated. Might not work, but you know what? It's going to be better than not trying it. So this is going to be a larger amount of time because we're going to raise the speed. This is just going to be d over r plus 10. Being the amount of time it's going to take. The amount of time d2 is going to end up being 1 minute lower than this time. Yes. Okay. So now we can get like a dr pair for all of these. Alright, so d over r minus d over r plus 10 is going to be equal to 1/60th. So the difference between these two times. Faster speed means quicker time, so that's the smaller value. Okay. So this is d r plus 10 minus d times r is equal to r plus 10 over 60. These can be factored, so we just get d times the quantity, r plus 10 minus r. It's going to be r plus 10 over 60. This is just 10. So 10d is going to be equal to r plus 10 over 60. D is equal to r plus 10 over 600. Okay, now I think I want to go the other way. Such that d is basically just a constant and r is the thing that actually matters. Okay, wait, this dr and this dr are going to subtract out, so we're just left with 10, right? 10d. Is equal to r plus 10 over 60. If this goes over here, it's 600d is equal to r squared plus 10r. This is a quadratic. This is a constant. That can just come over there. It's going to be 0 equals r squared plus 10r minus 600d. Might be getting a little far afield, but we'll see where this goes. Alright, so r is equal to, this is negative 10 plus or minus square root of 100 minus 4, a is 1, c is negative 600d. All over 2 times 1. 100. This is going to be 2400 d. You can factor out 100 from that, knock it out, and it's negative 10 plus or minus 10. Square root of 100 is 1, plus 100 out of that is 24d. All divided by 2. We can take that one out. We can knock out 2 from each of these things. Already took that one out. So again, these are like pairs that we've got. Negative 1's just not going to matter. Alright, so let's just plug in I mean, it's not going to do what we want, right? Because that's just going to be like, oh, it's a distance. If we plugged in 60, what does that do? 60 times 70 over 600. 7. That's 7 miles. And if it's 65 times 75 over 600, it's 8 1/8 miles. So yeah, it's getting like weird stuff back. So we're not doing quite what we want here, but interesting distraction anyway. What if it was this though? So d is equal to r t1, just t. That's fine. We got it. And same distance is covered in at r plus 10 miles an hour in t minus 1 minutes. So RT is then going to be equal to R plus 10 T minus 1. Like this is the equation we want because it relates our speed and our time rather than doing anything with the distance because the distance is just a constant, so just throw it out. I mean, it's not thrown out completely, but in this particular case, this is a system of equations. We've just put some stuff in. RT is equal to RT plus 10T minus R minus 10. All right, this is gone for 0. T minus 10 plus R on the other side. So in order to increase okay, so in order to increase our speed by 10 miles an hour and decrease our time by 1, crap, I did it again. I need 1/60th. So this is going to be minus 1/6. I also didn't rate this at all last time, so good thing. And this is going to be a 1/6 R. 60th. 60th. 17, 1/6. Minus 1/60th R. Move it to the other side. Plus 1/6. Move that over each. I just got 10T left, so T is going to be equal to the time that we need to increase. No, this is going to just be the overall time for our whole trip. Ugh. 1/60th minus plus 1/600th R. So if we do 60, it's going to be T is equal to 1/60th plus, that's going to be, this is maybe not what I want either. Hooray. 1/10. So that's going to be 6. Yeah. 60th. So it's like the final distance that we need to travel is 7 minutes before this is going to be even feasible. So I think I'm doing something wrong here, but that'll be cool. We'll figure it out at some point. All right. Let's see. I guess, does anyone have any last requests here? All right, let's rate Dev. Haven't done him in a while, so he is playing Dead by Daylight, and his stream is marked mature. So just, you know, with caution. We're gonna head over and see Div. Hope you all have a good rest of your week. We'll be back on Friday for games. We'll be picking up more Astroneer. We already finished the main story quest, so we'll be doing some other stuff that's all really cool things, including the Wanderer update, and we'll try to figure out the... I know how to do the Wanderer update, so it's not terribly difficult, although time-consuming. And I don't know how long the snails will take, so we'll see how that goes. At any rate, be thinking about some questions, do some really awesome, cool stuff, and we'll see you hopefully on Friday or next Tuesday for mathy type stuff. Have a good night, everybody. This is Obi-Wan Pez for N Simplex Pachinko. Good night.